Okay, class, here we are again. This will be lecture 2 in our compressed air series. Okay, so we were talking about different types of compressed air dryers at the end of the previous session. And, we really have two that you see out there in the field. The one being the refrigerated air dryer, and the other being the desiccant. So just to kind of review, the desiccant will get you a nominal dew point of the compressed air in the pipe of minus 40 Fahrenheit. Now, I've seen at Honda in Marysville, Ohio, they're painting lots of cars, and they actually use both a refrigerated air dryer as the first stage and a desiccant dryer as a second stage, and they were achieving dew points of minus probably 75 to minus 100 Fahrenheit. It was overkill, but when you're painting cars, you don't want to take a chance of screwing up. But anyway, the desiccant technology basically can strip tremendous amount of moisture out of the air. It's expensive to purchase, and it's expensive to operate, as we'll see in later slides. The refrigerant-type dryers, as we see a schematic depicted here, basically a small refrigeration system, and the air is put across a cooling coil and cooled to someplace between 35 and 38 Fahrenheit. And then it's reheated a little bit before it goes out in the pipes, because if you put 35 to 38 degree air in pipes being distributed around the plant, it's going to sweat like crazy, especially on the outside of the pipe in the summertime when it's warm and humid, and you're going to have drips every place, which would be a safety hazard. So it has to be reheated a little bit. I'd say they probably get it up in the 60s. Something like that, which you can put in a pipe, and then you're not going to have any condensate forming on the outside of the pipe just from the ambient air condition. Okay, with all that being said, let's take a look at this simple schematic of this refrigerated air dryer. So over here, this is the inlet to the dryer. So this is coming out of the discharge of the compressor. Spec on this is probably, generally speaking, just nominal terms, 100 degrees Fahrenheit and 100 psi. Could be a little higher, could be a little lower on the temperature. They don't like it to be much higher than 100. It'll start to derate the capacity of this thing. But first thing it does, it goes through this heat exchanger. So, we've got energy coming in, we got this warm air stream, we really want to cool down. I mean, our point is to cool this to 35 to 38. And so on the other side, we have air that has been cooled in the air coil or the heat exchanger down here. So this is cold. This is 35 to 38 down here. This is just a separator. And so we got cold air here we want to heat up. We got hot air here we want to cool down. So it's a perfect application for a heat exchanger. So that's what happens. The cold air comes in on this side and picks up heat from the hot, moist, compressed air coming out of the air compressor. So this guy gets cooled down and this guy gets heated up, and everybody's happy, I guess. So then this is the nominally 60 degree air, 65, whatever, that goes out to the plant or maybe to a filter or something before we send it out. And this is the pre-cooled compressed air, which is now lower in temperature. We show a separator and trap on both sides. It depends on the manufacturer. Some, you have to have this one for sure. Some manufacturers may or may not have this. They may want you to spec it upstream, whatever. And so then this air has been pre-cooled, but it's still pretty warm, and it's got a lot of water vapor. It's essentially saturated when it comes in. So that would say the relative humidity is 100%. on this side. So when we start cooling it down, we're going to get some moisture out of this, and then we come through. That's why that would be the point of having a moisture separator here. We'd like to go ahead and get that out if we've already condensed it. And then when it gets in here, it's still going to be saturated. And so as we cool it down, and this doesn't show the refrigeration system, which I'll show in the next couple of slides, it cools down to, like I said, nominally 35 to 38 here, and we wring out a lot of moisture here. So we drain some from this, and then we put it through a separator, pull out any drips, droplets, whatever, probably a cyclone type device. So we see removal, liquid water removal down here. This is the cold air that's dry, but it's, at saturation at the low temperature. We preheat it, and it goes out to the system. Okay, so the next two slides are one system. You can't, if you try to put it all on one, it gets so small that you can't read it, so I had to break it into two sections. So this is half of a refrigerant-type dryer, and I think I stole these mercilessly from Ingersoll Rand. Most of the manufacturers make this. This is what's called a thermal mass type dryer. And so the thermal mass is down here inside this tank. And the thermal mass is usually glycol, because 35, 37, 38 is pretty close to freezing. And we want to make sure that we don't freeze this thing up. So the glycol and water solution, the more glycol, you can lower the freezing point to 0 or below. So you don't have to worry about, that's Fahrenheit. And so we don't have to worry about freezing this tank if it's glycol. So this is the refrigeration side, and this is just a typical refrigeration device. We have a compressor. So the gas comes in on this side, and then we compress it so it's hot superheat through here, goes down to a condenser. So this is the high pressure side of the compressor down here. So this is superheated vapor. We cool it down in the condenser, condense it to a hot saturated liquid, filter dryer. Then we go through an expansion valve where we drop pressure, and you can see the color turning more blue. This is a little bit of a pressure drop, so we get a little bit of flashing to the vapor state, which cools down everything. And then this is a big pressure drop, and so I'd say 3 to 5% of this refrigerant flashes to superheated vapor. The rest is, I'm sorry, saturated vapor, and the rest is saturated liquid that cools down the whole flow of refrigerant to it could be between 25 and 30 degrees. It's good and cold, and then it flows into the heat exchanger here. Lost my pointer. There we go. If I don't keep this thing moving, it disappears on me. And so this is the heat exchanger. And so this boils off energy from the glycol, goes into the heat exchanger on this side, boils off the refrigerant, which is the cooling effect that keeps this glycol at the right temperature. And then this is superheated vapor that travels back to the compressor. A little review of your thermal one on this stuff. Okay, the other side of the heat exchanger, this is a loop, and there's a little pump on the other side that we'll see on the next slide, and it just circulates this cold glycol to another heat exchanger that actually cools the air. So there's a little pump in here that's pumping back through this side of this heat exchanger, because this stuff's going to come back a little bit warmer, because it's actually the flow that has cooled the air down, and so then it goes blast out here into the tank. And so that's how this is getting cool. And then the pump pulls it and circulates that side of it. Okay, so this is coming out of the glycol side of the heat exchanger in the first tank. Here's our little pump. it pumps through this heat exchanger. And on the other side of the heat exchanger, this is where our moist air stream enters. This is the heat exchanger that pre-cools it. So it comes in hot, it goes through this heat exchanger, and it's pre-cooled on the other side with the air that's leaving the dryer, which is cold, 35 to 38. So that air goes through on this side and comes out warm, probably in the 60s, so we don't get condensation in the pipes. And then this is the red is the compressed air, moist, saturated, coming in from the compressor. So this is where it gets preheated, and then it comes down here to the main heat exchanger where it is cooled down to the 35 to 38. And so then it travels over here to the moisture separator. So we get the bulk of the moisture out here. And so then it goes up for preheating and out to the system. So, you know, that's pretty good. So it's good to uncouple these, because if I go back up here, as long as this tank, you know, we may not be drying much air, in which case we're not heating this glycol up very quickly, which means this compressor doesn't need to run very much. And so when you decouple these things, so the refrigeration system maintains this temperature, and then we take that cold glycol off to another heat exchanger in order to do the cooling of the air and the removal of the moisture. It saves energy. The older systems, this thing operates just all the time, and you don't have this thermal mass involved. So this costs a little more on the front end, but is a whole lot more efficient. So if you're going to go for a refrigerated dryer, I think, as far as I know, this is kind of the best concept that's out there. Okay, so this shows some specifications on, again, I steal a bunch of stuff from Ingersoll Rand. All the manufacturers have stuff. So this just shows different models of dryers. The number over here in the model is the nominal CFM capacity. So this guy, the smallest one they show here would be for nominally 200 standard cubic feet per minute. And you see when you get air capacity right here, it's 200. And on the metric side, that translates into 5.7 normal meters cubed per minute. So different units for SI and US. We show a pressure drop in either PSIG, gauge pressure. Well, pressure drop is going to be really a differential pressure. 1.6, or in terms of BARG, it's 0.11. Operating KW, you see that the air-cooled, so this includes a fan in it, and so it's 1.66 kW for this little guy versus a water-cooled unit, and this is on the refrigeration system in the Desiccant dryer. So, you know, you could have an air-cooled condenser in there or a water-cooled condenser, and so, you know, you're not running that fan, and you may get a little better heat transfer in a water situation than an air situation. So now, if you're going to do water cooled, there is a pump someplace that has to pump that, and they don't include the pump energy here. So it's not the whole picture. Not really probably a totally fair comparison, even though we can move liquid for a unit mass a whole lot more with efficiently or with less power than we can move air. So anyway, dimensions, shipping weight, and just the size of the connection where the pipes connect in. And so we see, gosh, we got a big guy down here at 8,000 CFM. And so you can compare and contrast. But, you know, remember this 500, this would nominally be what we would put with a 100 horsepower compressor, you know, because we're what, between 400 and 500 CFM. So that would be the guy for that. So, you know, what if say we're 20 kW per 100, so that would be 500 nominally for 4.5 to 5. Let's say it's if it's rated for 500, so that would be 5 times 20 would be 100 kW on the compressor. And so the dryer is going to add another between 4 and 5 kW in this case. And we'll talk about the Desiccant later. Okay. Now, we said these dryers are nominally sized for 100 psig inlet pressure from the compressor at 100 degrees Fahrenheit, and sitting in an air compressor room that's 100 degrees Fahrenheit ambient environment. So we say these are rated for 100, 100, and 100. And so you see what those hundreds are. If the design condition is different, it's going to affect the dryer capacity and must be calculated using these correction factors below. So we have a little example here. So let's say that we have that 500 SCFM of compressed airflow that we need to dry, but the inlet temperature is 110 coming out of the compressor. Maybe that heat exchanger is not working too well, or maybe we put higher temperature air into this than we're really supposed to. I don't know. But coming out of our compressor, we're saying it's 110, and we're at higher pressure. This may be a 2-stage machine, and our set point is 125 psig, and it does sit in an ambient condition maximum of 100. So we want to see how, because normally we would select that dryer for 500 SCFM, but these two conditions are going to affect the capacity, and so we may need a different dryer. Okay, so the manufacturers publish these correction factors, and it's easy to get these tables, or the sales rep is happy to do this calculation for you. But we're engineers, so we want to do it for ourselves. So here's a correction for the inlet air temperature. And so at 110, we read a correction factor of 0.81. So we file that away down here, which we'll put it in our little equation. The 125 inlet pressure gets a correction factor of 1.08. That goes in the equation. And then the 100 degrees, that's the standard number, so there's no change. So we get a correction factor of 1 for that. Okay, so what you do is you take this nominal, or this 500 SCFM out of the compressor, and you divide it by the product of all 3 of those correction factors. And you see when we do that, that math produces 572 SCFM, so we always round up. So we would buy one size larger dryer for this in anticipation of these more aggressive inlet conditions. So pretty straightforward, but it's kind of interesting how that works out. Okay, so that's the end of our refrigerated dryer discussion. And we'll move on to the Desiccant here. So regenerative, what the regenerative means is that the way these are set up, excuse me, they have twin towers. And so one tower, both of the towers or tanks are full of desiccant. So we will dry on one tower, and we will regenerate or drive the moisture out of the second tower while the first tower is drying. And then on some sort of an interval, we switch. And so they just keep switching back and forth so that the dryer can continue to produce, the dry compressed air that the system needs. So again, we have on these ratings, we say that these are rated for 100 PSIG, 100 inlet, and 100% relative humidity. Excuse me. Pay attention to inlet temperature. It's very critical in the operation of these. You don't want to go above. This is coming out of your compressor. You'll affect it. It won't operate as well. Uses a porous desiccant. So this is adsorption, ADSO or BS or TION. which adsorbs moisture, which means it just the water vapor molecules just kind of stick to it. It has lots of cracks and crevices, and it has a low vapor pressure. So the moisture in the air has a high vapor pressure, and so it just basically sticks to it until it becomes saturated, and then all of the sites that a molecule could stick to are occupied, and it can't absorb anymore. So then we have to regen it, or we have to drive that moisture out. And we'll talk more about that in just a second. So it provides really low dew points. We're saying minus 40 down to maybe minus 100. I'd say our compressed air probably won't see temperatures that cold, so we would not have to worry about condensation if we dry with a desiccant. The problem is they're more expensive to operate. So generally used for process, instrumentation, outdoor applications, painting. You want very consistent, not much moisture at all in the compressed air that are used to spray on paint on cars, for example. Lots of specialty applications that need these sorts of things. Or lots of plants where pipes run outside. And, if they do that, then in the wintertime, if it gets cold, you're going to get below 32 quite a bit. You can have issues. Okay. One possibility, instead of drying all of your compressed air to this low of a dew point, would be to generally dry to with a refrigerated dryer that would get us a 35 to 38 dew point, and then put some small desiccant dryers at a particular application that might need drier air and not dry the entire compressed air stream to this low a dew point. Something that can be considered. They make the real small ones as well as large ones, and so that can work. Pre and post filtration is required. It's easy to foul this desiccant, and if you get a bunch of crud in those pores on the desiccant, a lot of times you can't get it out, and then you just have to replace it. And replacing desiccant's fairly expensive, so you'd like to only do that. The standard's about every 5 years. But for example, this desiccant loves oil. And so if we have a lube injected compressor, we really want to try to filter out any oil at all before the dryer to protect our desiccant, or we're going to wind up replacing it much more frequently at some fairly significant cost. So that's what it's saying here. Keep oil away from desiccant. Desiccant loves oil. And once you get it in it, you just have to throw the desiccant away. Okay, so this is the most basic, the cheapest to purchase of the desiccant dryers. So we show an air compressor here, and we have an aftercooler that's typically part of the compressor box itself. We're showing a separator and trap to go ahead, because this is we're gonna be 100% saturated coming out here. So there's gonna be moisture droplets in this, so we want to get those out. Then we go into the first tower we're showing here, which is doing the actual drying. Okay, so the moisture is being stripped out here. So this is all of our compressed airflow. And we get over here, and we have a valve that opens, and 15% of the rating of the rated CFM on this dryer gets tapped off here and bled through the second tower to regen it. So this stuff, we've paid all this money to operate this thing, to generate it. We dry it here, it's ready to go out to the system, and then we take 15% and we put through here. So if this is a 1,000 CFM dryer, say we've got a 200 horsepower compressor back here, and this is the dryer for it, of our 1,000 CFM, if we're at full load, we're going to take 150 of it, and it's not going to go to the system. It's going to get bled through this tower and thrown away to the atmosphere to strip off the moisture, so that we can, switch this in whatever length of time, and this become the drying tower, and this tower gets regened. And so that's the real cost of this, is you're throwing away 15% of the dryer rating almost continuously. And so, it takes a bunch of energy to generate that compressed air, and then we have to throw 15% of it away. So this is significant. But anyway, so that's the cost of doing business with a heatless up here, Desiccant Dryer. In moving up the food chain a little bit in terms of purchasing Desiccant dryers, we have what's called an exhaust purge. And so it's the same setup on the front end, compressor, after cooler separator into a drying tower. And now what we do is we still bleed off the dry compressed air, but it's down to 7% because we put a heater on it. Well, that's good. That's less compressed air, but we've got to spend energy. Typically, these are electric resistance, which is expensive energy. It can be hot air. It could be steam. It could be a waste heat source, which would be really nice, which would reduce the cost of operation. But I'd say 90% of the time, this is just good old strip heaters, which are pulling electric energy and heating this compressed air before it regens the tower. If you get it hot enough, nominally 250 degrees or above, which so there's, that's a fair amount of heat, you don't need as much. So you need roughly half. We said 15% before, now we're down to 7%, but we're still, so if this is 1,000 CFM rated dryer, we're going to pull 70 CFM, we're going to heat it up to 250 or 300, and we're going to run it through this tank. And of course, this tank gets pretty hot if you got 250, 300 degree air going through it. So it's recommended to insulate these towers on the heated dryers. Even though you don't see a whole lot of people that actually do that, it's a good recommendation, not only to save energy, but to keep personnel from burning themselves if they happen to bump into this. Okay, next up on the food chain, we're getting better, but we're getting more expensive. Same setup on the inlet, drying tower. Now we don't bleed any compressed air. We put it all out of the system, which is really good. And what we do is we take ambient air. We have a small blower that blows through a heat exchanger. So we heat up that air with ambient air, and we regen the tower with this. So this is better. We have to put a little electrical energy into this, and then whatever our heating medium is, probably electricity, but it could be natural gas fired, or it could be a steam coil, whatever. And then this stream it just takes from the compressor room, goes through the tower and gets vented to atmosphere, taking all the moisture that we're pulling out of this tower and getting rid of it. Okay. All right. And the last, and you don't see many of these, this typically is purchased with a compressor, so it comes as a package. But it's kind of an interesting technology. What we do is when we come out of the air compressor, we have pretty good temperature. Now, it depends on which compression technology, and you have to be a little careful that you get enough temperature to make this guy work. But so a note here, this has to be greater than 250 degrees, but you put that directly. And so this is laden with moisture. We haven't gone through the after cooler. There's a boatload of moisture in this thing, but we go ahead and we pull it in the regen tower. And so we're pulling more moisture out of this tower. So this stuff really, of course, at 250 or greater, we can hold a tremendous amount of water. And so it's not close to, this is not close to saturation because it's so hot. And then we go here, so we strip out this moisture. And then we go to the after cooler, and it rains a boatload in there. So we take out not only the vast majority of the moisture that goes through the air compressor, we strip off the moisture in regenerating the tower, and then we have to condense all of that, or the vast majority of it here, and then we put it through a separator and get the liquid water out of the separator through a trap, and then we go through the drying tower. And so it goes out. So we got our minus 40 dew point over here. So we don't waste any air. We don't put in any extra heat. We use the heat of compression of the air compressor to provide the energy, because that typically just gets thrown away. So this is a very efficient arrangement. The only extra cost is that the compressed air has to go through both towers. So we have a pressure drop on this tower, and we have a pressure drop on this tower. So, and that's probably not all that great. That may be a couple extra PSI. So we may have to set up the the discharge pressure on the compressor in order to accommodate that. Okay. I've got some really detailed slides here on this heated compression. There's characteristics of it and all that sort of thing. I don't think I'm going to talk through all of these. I think you should read these on your own. And, you know, we've got a little bit better graphics. This shows the air coming out of the, I lost my pointer again. There we go. Out of the compressor. So that's regen that tower. Water cooled. Well, this is showing a water cooled heat exchanger and moisture separator. But then we go through the second tower where we dry it and out to the system. So anyway, you can read through these on your own. Okay. I'm going to let you read this one too. I don't want to talk through all this on this slide. So there's some operating issues and some other, a little more detailed, but basically I think I've described it pretty well. Okay, this shows some pictures. This is the heatless. You look between the towers, and if there's nothing but some valves and all that, then it's a heatless. So it's the cheapest dryer, but that's the 15%. We look over here and we see you've got some hardware in here. If you look at it, it's going to be some sort of a heating system. And so that's next up. So this is going to vent 7%. This is the blower purge. You look on the back side and someplace there'll be a blower like over here or over here, and that tells you, and then there'll be a heater. And so you look for that. And then we already illustrated the heated compression pretty well. And this is kind of old, this deliquescent. You don't see those anymore. It gives you some kind of an idea. The relative operating cost. This is dollars to dry 1,000 standard cubic feet per year. I think this is based on 5-cent electricity. And so you see the dew point and the relative operating cost. So see, this heatless desiccant dryer cost you a boatload, and that's because you're venting that 15%. The heated compression is 2,000, so that's even better than and this is the heat recovery standard dryer. This is the refrigerated dryer that just runs all the time. So you see the thermal mass reduces operating cost. But this heated compression dryer is pretty darn good. But the problem is that you have to retrofit a compressor, or so basically when you buy an air compressor, if you want that, you buy it with it. Okay, guys, that's enough for this time, and I'll probably post one more later. Thanks.